Okay. All right, but like I say, we're starting with identities tonight, or we're looking at identities tonight, and therefore proving them. So guys, if we have a look at this first example, the first thing that I want you to remember about proving an identity is the fact that when proving an identity, we're not going to already assume that the left is equal to the right. So essentially, we're not really going to assume that it is an equation or a true equation. When we prove an identity, we need to essentially pick a side that we are going to manipulate to make it look like the other side. So if you choose to manipulate the left, you eventually want it to get to look like the right. If you want to manipulate the right, you eventually want it to get to look like the left. That's the idea of an identity. So remember, you are proving that the two sides are equal. You are not already assuming that they're equal and working with them as an equation. Okay, so when it comes to deciding which side of your identity or of the expression that you've been given you are going to manipulate, there's a couple things to look out for. I usually say if there's a tan, that's probably the side you're going to manipulate. But now at a grade 12 level, there's a few additional things we need to think about. We need to think about the fact that we have double angle formulas. We need to think about the fact that we've got compound angle formulas. And so when it gets to a grade 12 level, we also need to start thinking about, can I actually do more with a double angle than I can with, say, for example, a tan identity? So if we look at this identity that we're wanting to prove here, we've got 1 minus cos 2 theta over sine 2 theta is equal to tan theta. So now we have to think a little bit. On the right-hand side, I've got tan theta. So absolutely, you could apply your tan identity, sine theta over cos theta, sure. But you can't do anything more than that. Sine theta and cos theta are as basic as they come. So we can't really do much more than that. However, on the left-hand side, we've got some double angles. And so that is the side I'm going to choose to manipulate because I've got all of these double angle formulae that I can apply. So just on the right-hand side of the screen, I've got my double angle, my compound angle formula here for you. Just in case you don't have a formula sheet in front of you, it's there. Right, so we're going to choose to work with the left-hand side. Note how I'm stating which side it is I'm going to manipulate. Obviously, you don't have to rewrite the side if you don't want to. I just find it easier for myself. But I've stated the left-hand side, that's the side I'm going to manipulate. Okay, when it comes to double angles, please remember that sine double angles, you've only got one formula. So I'm going to start with changing my sign. Yes, I'm going to have to change the cos 2 theta in the numerator, but there's 3 options, and I'm not too sure which option I'm going to go with yet. So I'm going to start with the sine, and then I'll go from there. So that expands to 2 sine theta cos theta. Right, now, when proving identities, the one thing you also always want to remember is, what are you actually trying to prove? So we always want to go back to the original expression we have and say, okay, well, what is it that I'm trying to do here? I'm trying to get this to equal tan theta. Oh, stupid thing. Now, tan theta, remember, is sine theta over cos theta. Now, the reason I need to bear that in mind is because right now on my left-hand side, I only have sines and coses. Right now, based on the fact that I have to have a sine in my numerator and a cos in my denominator, this is now going to help me decide which cos double angle formula to use. Right now, I've got a cos in the denominator, but I also have a sine. I also have a 2. At some point, those things are going to have to cancel out because I don't want them there. I just want the cos theta in my denominator. So what that means is in my numerator, I'm going to have to pick a cos double angle identity that hopefully has a 1 that cancels with the 2 that I have there. I know that doesn't make much sense, but essentially I need to get rid of that coefficient of 2. Or I want to have a situation, I don't know, my brain just had a brain fart. So in my numerator, I want to choose a cos double angle that is going to allow me to introduce the sine theta that I want in my numerator and help me simplify away that 2 sine theta that I don't want in my denominator. So what that means is I want to choose a cos double angle that contains sine. So either that's the first option or the last option. Now, this last option already has a coefficient of 2. That's great. It means it's going to cancel hopefully with that 2 that I have there. This last option also only has sine. In the first option, I would then be introducing a cos squared. Why? Why introduce more than what we need? So I'm going to go with my first option. So I've got 1 minus, and I'm going to replace this cos 2 theta with the double angle formulae that I've decided is most appropriate. 1 minus 2 sine squared theta. My denominator I've already sorted out, so I don't need to stress about that. And remember, what you're now going to do is you're going to distribute in that -1. So 1 minus 1 is gone. Minus times a -2 is now 2 sine squared theta over 2 sine theta cos theta. And we can simplify. So what ends up happening is we are able to divide the 2's away. 2 divided by 2 is 1. 1 sine theta can divide with the sine theta in my numerator and my denominator, leaving me with sine theta in my numerator, cos theta in my denominator. Now remember, we said that that is the tan identity. So this can be written as tan theta. And so what we've proven is that the left-hand side is equal to the right-hand side. And that's essentially how we work with proving an identity. We want to make it equal. We want to manipulate one side so that it represents or is identical to the other side, to then state that those are equal, to then state that the statement originally made is true. So like I said, there's unfortunately not like a formula I can give you that says if you follow these 3 steps, you're going to solve any identity. It doesn't work like that. We need to just look out for certain things. We need to look out for our double angle formulae. We need to look out for our tan identity sometimes. We need to look out for our squared or Pythagorean identity sometimes, which is sine squared plus cos squared equals 1. We need to look out sometimes for factorization. So there's a few things that we need to bear in mind as we are starting to prove identities. Okay, now guys, please remember, if at any point you have questions, please just ask. Because like I say, I get that identities aren't necessarily the easiest thing in the world, but we do need to be able to answer them. Okay, another thing with identities, just remember, always go back to what it is you're trying to prove. So like I say, we were trying to prove that it's equal to tan theta. So always keep going back and saying, okay, this is where I am. How am I going to get to that tan theta? What do I still need? And that's essentially what I was asking myself the whole time. I knew I needed to have sine in the numerator, cos in the denominator. How was I going to get there? So as long as you keep referring back, you can sort of guide yourself in the right direction that you need to be going in. Okay, but let's take a screenshot and then we will have a look at a second example. Okay. All right, so if we have a look at example 2 here, we have been asked to prove that cos 2x divided by cos x minus sin x is equal to cos x plus sin x. So first thing we want to do is decide which side we're going to manipulate. On the right, we've just got cos x plus sin x. I can't really do anything with those. Unless I want to manipulate them with the tan identity, which is just going to be gross, because then I'm introducing tan, and why introduce tan if I don't have to? I'm probably going to look at the left-hand side, and I'm even more drawn to the left-hand side because of that cos double angle. So I'm going to manipulate my left-hand side here. Right, now the next skill you need to start developing with identities is the ability to look at what you've been given and understand where they've come from. So this cos x minus sin x, it's a very aggressive highlighter. Take it down a notch. This cos x minus sin x and this cos x plus sin x. This should be reminding you a little bit of factorized expressions, even more specifically, difference of squares or quadratics, trinomials. Okay, if you're not too sure where I'm going with that thought process, have a look. If you were given x squared minus y squared and told to factorize it, you know that that would give you x minus y, x plus y. That's what you have here. You've got cos minus sine, cos plus sine. You have a factorized set of things going on. Now, granted, they are on two different sides of the equation, but because I can see that there's a link, that there's a relationship, and that's through factorization. Like I said, it already is starting to guide me to where I need to be. Okay. So based on that, and based on the fact that I've decided I'm going to work with the left-hand side, I now need to decide which is the most appropriate cos double angle formula to work with. Now, I've just said we want to be able to factorize. I can't factorize 2 cos squared a minus 1, and I can't factorize 1 minus 2 sine squared. Unless we had some more terms going on to create a trinomial, that's not going to happen. The only one I can factorize straight off the bat is the cos squared minus sine squared, because that's the difference of squares. So that's what I'm going to change this to. Cos squared x minus sine squared x all over, whoops, apparently we wanted an arrow, all over cos x minus sine x. Like I say, in your numerator, you now have a situation where you've got the difference of squares, so we can factorize this. That factorizes to cos x minus sine x times cos x plus sine x all over cos x minus sine x. And what I now see is that the cos x minus sine x brackets divide away. They become 1. And so all I'm actually left with here is cos x plus sine x. And if you refer back, that is the right-hand side. So I've proven that the left-hand side is equal to the right-hand side. That's it. So again, you need to start looking at identities in the light of almost thinking already 2 steps ahead of yourself. If you can start to see where terms have come from, where expressions have come from, and you can figure out a way to get there, oh, I can factorize this thing, or I can replace this term with this identity or this formula and get to where I need to be. That's going to be your greatest skill when it comes to identities. Again, it's not something that happens overnight. You're going to have to practice these, okay? It just is what it is. I've given you past paper links. But if you practice this stuff, you start to get more and more comfortable with the relationship between your terms and what it is that you're trying to work with. Right, so take your screenshots. Again, guys, if you have questions, please just ask. You're welcome to unmute. You're welcome to put it in the chat. You can send me a direct message, whatever you're more comfortable with. But once you've screenshotted, I'm going to put one up that I want you guys to try by yourselves. Okay. So I want you to try this one by yourself. I put your double and compound angle formulas here on the side for you in case you want them or in case you need them. So give this one a try for me. I'm going to give you 5 minutes. It should be enough time, but I'll check in with you in a second to see if you need more. 5 minutes, let's see how we go. And remember, if you've got questions, just ask as you go along. It seems one or two of you are already done. There may very well be more. I'm going to give you 1 more minute and then we're going to have a look at our answer. There's often more than one way to do this. I've put 2 methods down. You can check which one you did. If you came up with something different, cool. These are the 2 I could see. Often there's more than one way to do this. Okay, it seems we are getting to be done. Right, if you're not done, don't stress, you can take a screenshot. Like I say, I saw 2 different ways that you could do this. Really depends what you see. So let's maybe try to get this all in one go. Right, so first option of how you could deal with this whole situation is you could have worked with the left-hand side. So the left-hand side, because of the square, you would need to distribute your brackets, which is what I did over here. Distribute, and then you need to start looking out for your identities. So cos squared plus sine squared, remember, is your Pythagoras or your square identity. That becomes 1. The 2 sine theta cos theta there in the middle is a double angle. So this reduces or simplifies to sine 2 theta. And so you get your right-hand side of your equation. Perfect. If you didn't do that and you worked with the right-hand side because you saw that sine 2 theta, that's fine. Sine 2 theta, as we've already discussed, becomes 2 sine theta cos theta. So a double angle formula that you can apply. But the problem is you need to get a bracket squared. Now, brackets squared come from factorization. So this 1 is your square identity. And then what you have here is a trinomial. Okay, so your trinomial is x squared plus 2xy plus y squared. If you imagine this is your x squared term, 2xy plus y squared, that is the trinomial that you need to factorize. Once you factorize that, it becomes the same bracket, so the bracket squared, and that bracket was cos theta plus sine theta. So again, the left is equal to the right. Both of them are fine. Both of them will earn you full marks, whatever you saw. Right, so out of interest, who manipulated the left-hand side? Who manipulated the right-hand side? In the chat, just put LHS or RHS for which one you did. I'm interested to know who did what. Or did you do something different? Kosi, Ati, Daniel, okay. Manual, a lot of left-hand sides. Yeah, I'll be honest, I probably would have done the left-hand side as well. I don't think I would have gone straight to the right-hand side. It's also a bit easier in my opinion. Very nice, guys. Well done. Okay. All right, let's have a look at another one. Oops. All right, so example 3 we've got here is we want to prove that 1 plus sine 2a over cos 2a is equal to cos a plus sine a over cos a minus sine a. So again, look at things that you can work with. Cos a plus sine a and cos a minus sine a. I can't really do anything with them. Okay, I could apply a tan identity. Like I say, don't introduce tan if you don't have to. There is no point to introducing stuff that we don't want to have to deal with. However, we know that these 2 expressions that I've highlighted there in green are a result of factorization. Difference of squares, trinomial or quadratic, They are a result of factorization. So in the back of my head, I need to be thinking about that. So I'm definitely going to be manipulating my left-hand side here. And I can see I've got some double angles I can start to work with. Now, because of the cos double angles, there's 3 options. I'm going to leave that for now. I'll deal with that in a second. But I can definitely change the sine 2a to 2 sine a cos a. Okay, all over cos 2a. Now remember, based on the preliminary assessment that I did, I kind of want to be able to factorize. In my numerator, I currently have 1 plus 2 sine a cos a, and I need to get a cos a plus a sine a. So I don't really want that 1 there. And I essentially want a situation that's going to factorize to give me a bracket that is cos a plus sine a. Right now, that's not going to do that for me. So what I need to remember is that this 1 is actually an identity, because remember, sine squared theta plus cos squared theta is equal to 1. If I replace that 1 with a sine squared plus a cos squared, and then I have the 2 sine a cos a, that's a trinomial I can factorize. So think about that. We already know, obviously, that my brain. We already know, obviously, that the cos 2a double angle, one of those formulae is a difference of squares, cos squared minus sine squared. So we can use that. I don't know why my brain took so long to get those words out, but it's fine. Okay, so the 1 I'm going to change to the cos squared a plus sine squared a plus 2 sine a cos a. I'm going to rearrange that to look like a trinomial just now. All over. And this cos 2a, I'm going to change the difference of squares formulae so that I can factorize. Cos a minus sine squared a. Right, in my numerator, I'm just going to rearrange those terms so it actually looks like a trinomial. So cos squared a plus 2 sine a cos a plus sine squared a. If you don't understand where that's coming from, remember trinomial, that's the key word here. So that trinomial is going to essentially be x squared plus 2xy plus y squared. That's what's happening over here. And then in my denominator, as I've said, difference of squares. So we will have cos a minus sine a times cos a plus sine a. I can factorize that trinomial. That becomes cos a plus sine a times cos a plus sine a. We also already knew that because we had this earlier with that bracket squared. All over my factorized denominator, which I'm not going to say again. And then we can start to see what can simplify, what can divide away. Remember, always go back to what you want. We need a cos a plus sine a in my numerator, which I now have. I've got 2 of them. And in my denominator, I've got a cos a minus sine a. I've got that, but I also have a cos a plus sine a. So I need to get rid of it. But that's perfect. It divides away with one of those brackets in my numerator. And so what I now have is cos a plus sine a in my numerator divided by cos a minus sine a in my denominator. And that's exactly what I wanted. The left-hand side is now equal to the right-hand side. Okay, so with identities, always remember that factorization is a very real possibility that you need to deal with, and start thinking about the expressions that you've been given and how they link to the factorization. Do they come from a difference of squares? Do they come from a trinomial? Could they come from either? And then how do you manipulate your double angle, your compound angles, whatever, according to the formulas that you have? All right, so let's take a screenshot. And then we're going to have a look at another example. Okay. Oops. So if we have a look here at example 4, we have been given, prove that sine 4 theta minus sine 2 theta over cos 4 theta plus cos 2 theta is equal to tan theta. Now again, guys, look at what you've been given. On the right is just a tan theta. Yeah, I could change it, but I can't do much more than that. So I'm probably not going to work with the right. On the left-hand side, I got a whole bunch of double angles going on here. What I want you to remember is that a 4 theta, sine or cos, it doesn't matter, is a double angle. Sine of 2 times 2 theta is a double angle. That also then starts to match up with the other angle that I have there. So always just, again, be looking at these things. Be looking at, okay, where has 4 theta come from? It's a double angle. Okay, what does that mean? Does it now match up with the angles I have? Yeah, it does. So maybe I can factorize things out. So you always just need to be having this like internal dialogue with yourself to figure out what's going on. So like I say, just based on what I have going on here, the left-hand side, pretty safe bet is the one I'm going to manipulate. Okay, now obviously remember that in order for you to start factorizing or really doing much, your angles need to be the same. So I'm going to start with the 4 thetas, those bigger double angles for lack of a better description. Sine 4 theta, I know I can expand to, work there, so we'll go here, to 2 sine 2 theta times cos 2 theta. And even though that minus sine 2 theta is a double angle, I'm going to leave it for now. Because like I said, what I now see is that in both terms, I've got a sine 2 theta. I can start to factorize. I can start to simplify what I'm working with. Right, in the denominator, I've got that cos 4 theta plus cos 2 theta. So again, I want to be thinking about the fact that I want to be able to factorize. And if you go back to what your end goal is, remember this is tan theta, which is sine theta over cos theta. I only want cos thetas in my denominator. So I'm going to try pick an identity that only deals, or double angle formula that only has cos in it. Because if I introduce a sine squared, I'm creating more chaos for myself. The only one that deals with cos only is the 2 cos squared a minus 1. So that's the double angle I'm going to go for here. So 2 cos squared 2 theta minus 1 plus cos 2 theta. So just remember that double angle for the cos 4 theta, that's what I've applied over there. Okay, so like I said, in my numerator, I can factorize. I can take sine theta or sine 2 theta rather out as a common factor, leaving me with 2 cos 2 theta minus 1. Great. In my denominator, I have a trinomial. 2 cos squared 2 theta plus cos 2 theta minus 1. That is a trinomial. Trinomial because we've got 2x squared plus x squared minus 1. That's a trinomial we can factorize. I feel like I'm saying trinomial so many times. All right, and now we can go and factorize that denominator. So Butle, I do see your question. I'll come back to you in a second. So let's just quickly factorize this and then I'll answer you. So in my numerator, I've already factorized, so I can't really do much more than that. And in my denominator now, remember, you've got this trinomial. So factorize a trinomial as you usually would. This ends up being 2 cos theta minus 1. Would also help if I wrote the correct angle. 2 cos 2 theta minus 1 and cos 2 theta plus 1 plus 1. There we go. Not the nicest looking thing, but we'll deal with it. Okay, hopefully you can start to see what can be simplified. You're welcome to go ahead and do it. I'm just going to go back to Butle's question quickly. So Butle asked, how do we identify which formula to use for cos? So Butle, it comes down to what are you working towards, right? So in this specific case, remember what I'm working towards is tan theta. So that means I need only, or I want only causes in my denominator. If you look at what you started with, you did start with a situation with only causes, but we had that double angle that we needed to deal with. So in considering my 3 double angle formulas for cos, I wanted to pick the one that only had a cos in it. The first one has a sine squared. I don't want to introduce a sine squared in my denominator because I don't want sine there. I don't want to introduce, obviously, the last one because that's sine squared again. So I'm going to pick the one that only deals with cos. Yes, there's a 1 there, but more often than not, the ones are going to cancel, or it's going to be a situation like this where it's a trinomial. So it very, very much depends on what it is you're looking for. If, for example, we go back to example 3 here, again, we had a cos double angle my denominator, but what I was aiming towards was different. I was aiming towards a denominator that had a cos plus a sine, or cos minus a sine. I was aiming towards something where I had both. So I needed to look at my identities and decide which one would give me a cos and a sine. That would have been my first identity. So you always need to be referring back to what it is you're trying to prove, back to what it is you're trying to get your identity to be equal to decide which one is which. Sorry, there's just someone at my door. So essentially, that's how you decide what you want to do. You go back to what it is you started with and you decide how to make it. All right, so based on what we have, we've got a double angle that we need to deal with. And we now have factorized, we've done all of these fun things, and now we need to go and simplify further. Okay, like I said, hopefully what you can see is that the cos 2 theta minus 1 divides with the cos 2 theta minus 1. And so this is the beauty, remember, of factorization. You can simplify. So now all we have is sine 2 theta over cos 2 theta minus 1. So Butler, your question is going to become important now again, because now we've got more double angles we need to deal with. Okay, now guys, the reason I know I also need to deal with these double angles is because remember my right-hand side has a theta. The angle I'm working with there is theta, not 2 theta. I have to get rid of those double angles. All right, so based on that fact, I now apply my double angle formula again. Sine is easy, I've only got one choice. Technology is fighting me. It's 2 sine theta times cos theta all over. Okay, so back to Butler's question. How do I now decide which cos double angle identity do I use? Okay, I only want cos in the denominator. That means I'm not going to pick the first one. It's got a sine in it. Don't want a sine. I'm not going to pick the last one. It's got a sine in it. Don't want it. I'm going to pick the one that only has cos so that I end up with only cos in my denominator. So this cos 2 theta, I'm going to now apply my double angle identity to make it 2 cos squared theta minus 1. And remember, I still have, sorry, that's a plus 1. I still have the plus 1 there in the denominator. And that's just what I said earlier. Those ones probably eventually cancel out, become part of the trinomial. We don't have to stress about the ones. It's very rare. We had an example earlier where we had to change the 1 to the sine squared plus the cos squared. It's rare we have to do that. Sometimes we do, but yeah, it's gone. Cancels out, no problem. So what we now have is 2 sine theta cos theta in my numerator divided by 2 cos squared theta. I can start to simplify. So what I see is going to happen here is that 1 cos cancels with 1 cos in my denominator. 2 divides with 2 in my numerator and denominator. And so what I'm left with is sine theta over cos theta. Remember, sine theta over cos theta is tan theta. What did I want my right-hand side or my left-hand side to be? Tan theta. So I've proven the left-hand side is equal to the right-hand side. So it's, like I say, unfortunately, it's not one of those things that I can say, yes, if you follow these steps, you're going to get it. And it sort of links with what Butler was asking, like, it does, the fact that there are so many options for the cos double angle, it does make it harder, but always refer back to what you want. In this case, because I knew I wanted a tan, I needed to keep that denominator only having causes in it. The question before I explained, we wanted a cos and a sine. So I had to choose the identity or the formula that was appropriate for the question. It comes with practice, guys. Sometimes I still look at things and I'm like, I don't know what you want. Like, what must I do with that information? But it comes with practice. Sometimes you're going to do an identity and you're going to get stuck and you're going to have to start again. But the more you practice, the more you start to identify things like, in example 3, that comes from, I'm saying that situation there, cos A plus sine A, cos A minus sine A, that comes from a quadratic. I need to have a quadratic. Tan, things are just zooming in and out, so we're just going to roll with it. Tan comes from sine over cos. That's what I'm wanting. It comes with practice. Okay, so take a screenshot. I've just got a question to re-explain how I factorize the denominator in step 3. I'm going to be honest, I don't even know where my own step 3 is. So are we talking about this denominator I've highlighted in yellow? Just give me a yes or no. Is this the denominator you want re-explained of how I factorized it? I'm assuming, okay, cool. Okay, so guys, people factorize trinomials differently. I remember at school, my teacher taught me the most complicated method of factorization. Some of it has stuck with me, but it was complicated. I remember when I first started teaching, I also taught us so complicated, like there's lots of different ways. Obviously, I think my way is the simplest way, because everyone thinks that, but as long as you can factorize a trinomial, hopefully you'll follow me. So remember what we have here, based on what we wanted, remember? So we went based off of what we wanted, using my double angle. I ended up with, I'm just going to write it here, 2 cos squared theta plus cos squared theta minus 1. Okay, that relates to an algebraic expression of 2x squared plus x minus 1. So if I take the algebraic one, just to sort of simplify the whole process, and I factorize that. So the way I factorize is I look at my first term's factors. In this case, it would be 2x and x. If I times those two together, I get 2x squared. And I look at my last term's factors. I've only got factors of 1 and 1. To factorize this, what I do is I cross multiply. So x times 1 is x. 2x times 1 is 2x. And then I ask myself, how do I get the middle term of plus 1x? Do I have to add those two together? No, because x plus 2x is 3x. I'm probably going to have to subtract. And it would be a case of 2x minus x. So the negative must be with the x, the positive with the 2x. Again, some of you have different ways of factorizing trinomials. That's fine. Okay, whatever works for you, this works for me. Some of you have calculators that can do it for you, whatever. So through my cross multiplication step, what I've gotten is that my brackets are going to be 2x minus 1, x plus 1. Now, if you have a look at what I've written down here, the x's relate to the causes. It is a cos 2 theta, so I do apologize for that. 2 theta, 2 theta. So this will be 2 cos 2 theta minus 1 and cos 2 theta minus 1. Because remember, the x's represented cos 2 theta. And so that's how I ended up with those two brackets over there. So again, grade 12s, if for you, it is easier to write the trig trinomial as an algebraic trinomial, factorize that and then just go back and replace it with your trig ratios, do that. There is nothing wrong with that, right? Generally speaking, you should say, let x equal cos 2 theta, but there is nothing wrong with converting it to an algebraic expression and then going and just replacing the algebra with the trig. If that makes it easier for you, do that. Okay, you'll see in memos that they often don't do that. Obviously, like a memo, generally they try and shorten as much as possible, but there's nothing wrong with that. So if you need to do in green the algebra and then go back to the trig, by all means do it. Alrighty. Okay, so I'm assuming we've all got screenshots. I'm just going to wait 10 seconds in case you want a screenshot with all of my scribbles on the side there. But I think you're going to try one by yourselves. Okay. Right, so let's give this one a try. Again, I've put all of the formulas down there at the bottom for you in case you need them. Again, I'm going to give you like 5 minutes. Let's give it a go. What I do want you to be mindful of is that this situation over here should be reminding you of something going on in this situation down here with the compound angles. That's all I'm going to say. So give it a try. Like I say, 5 minutes, and then we'll look at the answer. Okay, guys, I'm going to give you like 1 or 2 more minutes, and then I'm going to put up the answer. Okay, let's have a look. So like I said to you, the key here is that you can see that there's a compound angle situation going on here. There seems to be some things missing. Just strange, but that's fine. No wonder. Okay, so you've got compound angles, compound angle formulas that you can apply here, because on the left-hand side, those are compound angles. So the cos x plus y should be reminiscent of your cos a plus b, cos x minus y, cos a minus b. We essentially expand. Not the nicest thing in the world, but it is what it is. Okay, sorry, that's supposed to say sine squared y that I'm trying to scribble in here. My pen's just been gross. Okay, so guys, from this first step, you need to distribute. Now, what you need to remember is that when you've got brackets of a minus b, a plus b, that's a difference of squares, which means that when you distribute to a squared plus ab minus ab plus b squared, those middle terms cancel. So that's why here I only distributed or multiplied the first and the last, because I knew the middle terms were going to cancel. And so this is where you need to start thinking about those relationships. Now remember, always go back to what it is you're trying to find. On the right-hand side, I only want sines. Except for that y, it's only sines. So that means this cos squared y squared needs to go. Cos squared y squared, remember, your square identity, sine squared theta plus cos squared theta, okay, it's just been difficult, equals 1, which means that cos squared theta is equal to 1 minus sine squared theta. That's what I've replaced each of those cos squareds with. And then I just have sines going on. Again, I would need to distribute those brackets, but I get terms that essentially cancel out, leaving me with exactly what I wanted for my answer, for my right-hand side. So again, all of this was algebra. Okay, this was just algebraic manipulation. Once you had dealt with the compound angles, it was just algebra. It was distribution. It was multiplying out, etc., etc. Okay, so a bit of a tricky one, this one. Hopefully not too tricky. But again, trig is manipulation. Manipulation often with algebraic concepts. If you know your algebra, you can do trig. So it's really important to go back to those algebraic basics and revise them. Okay, guys, we take your screenshots here. Unfortunately, we've got 4 minutes left and it's not quite enough time to do another example. So once you've got your screenshots, you are welcome to log off. I will see you on Monday where we're going to do some equations, some general solutions with all of this trig stuff that we've learned. And then obviously it's your last quiz for the trig section. If you don't have questions, like I say, once you've got your screenshot, you can go. If you do have questions, you're welcome to ask. Like I say, we've got like 3-4 minutes left.